So to finish this chapter, we are going to construct an explicit unconditional basis of LP of 0, 1 for p strictly between 1 and infinity. This basis is called the Haar basis. Now, the existence of unconditional basis in L2 of 0, 1 is pretty clear. You can take any orthonormal basis, for instance. But when p is not equal to 2, it's not even clear that we do have a unconditional basis. So we'll construct one. And the basis is given here. The first element, you take the indicator function of all of 0, 1. And after that, you take this weighted difference of indicator functions. So the simplest thing to do here is to draw a little picture. Here is what this basis look like. So the first element, E1, you take your interval 0, 1 and you split it in half, 0 to 1/2 and 1/2 to 1. And then you put something that is a multiple of 1 on the left-hand side and a multiple of -1 on the right-hand side here. And this difference of indicator functions. Now, the actual multiple, the actual height of this is, in that case where I've taken k equals 0, this would be actually 1 and -1. But then on the next level, if I take k equal to 1 rather than 0, then I'm going to have things at the level 2 to the 1 upon p. And so that's going to be here. And we're going to have something, the first one will be 1 up to 1/4 and -1 up from 1/4 to 1/2. So that's E1, that's E2, and then we have E3 will be, if this is 1/2 here, it would be 2 to the 1 upon p here and -2 to the 1 upon p there. That's E3. And then we keep going like that. We decompose the interval 0, 1 into dyadic pieces of side lengths 2 to the -k, and then on any one of these dyadic pieces we put a function which is 1 half of the time and -1 the other half of the time. Well, not quite 1 and -1, but 2 to the k upon p half of the time and -2 to the k upon p the other half of the time. Now, the reason for this normalization here is just such that the LP norm of any of these En is 1. Right? So I've normalized them in LP. Okay, now associated with these vectors, we're going to have a family of bounded linear operators that are going to be the projection onto the partial sums of a series decomposition. And they take a very explicit form. And here it is. We have these operators E to k that take a function and does the following, right? On any interval, so you fixed a scale 2 to the k, and then on any of the intervals that corresponds to decomposing 0, 1 in intervals of the size 2 to the -k, you replace the function by its average over that interval. Right, so this is really a operator that sends a function, general function f, to a simple function, and that simple function takes 2 to the k values, and on any one of these 2 to the k intervals of side lengths 2 to the -k, you replace the function by its average. Now, those of you who do probability will recognize that this is a conditional expectation. It's really projecting from L2 of 0, 1, let's say, or LP of 0, 1, down to LP of 0, 1, endowed with the sigma algebra that is generated by these finitely many intervals. So that's one way to think about this operator. But we are going to show that this is really a projection map corresponding to projection onto the first few terms of the decomposition into these vectors seen as a basis. So this is the theorem we want to prove. We want to prove that this particular sequence does form a basis of LP of 0, 1, and that this basis is unconditional. So there will be 3 steps. First, prove that it's a basic sequence, then prove that it's a basis, and then the really hard step, prove that this basis is indeed unconditional. Okay, so let us prove that the Haar system is indeed a unconditional basis of LP of 0, 1 for p strictly between 1 and infinity. Now, let's start with the fact that it forms a basic sequence. And the fact that En is non-zero for all n is obvious. That's because we've normalized all of these things to be to have norm 1. And also, I mean, they're just differences of indicator functions. They're really just none of them are the zero function. So that's obvious. Now, let's have a look at what happens when you apply partial sums projections. So in order to understand that, we need to understand the role of the operators e to the 2k better. So what happens if I look at e to the 2k applied to a basis vector e to the 2l plus j, and let's say that I have a k and a l in n, and I have a j that is somewhere between 0 and 2l minus 1. And then I'm going to assume that my l is greater than k. So what happens in this case where L is greater than K? Well, let's write up what this is. This is the sum for M equals 0 to 2K minus 1 of these indicator functions of, what is it, M 2 to the minus K till M plus 1, 2 to the minus K, say at a point T, okay, times 2 to the k times the integral from m2 to the minus k to m plus 1, 2 to the minus k of e 2l plus j. Now, but what is e 2l plus j, right? It is a difference of two indicator function times 2l upon p. So indicator function of of j 2 to the minus l till j plus 1/2 2 to the minus l minus the indicator function of j plus 1/2 times 2 to the minus l till j plus 1 2 to the minus l. Okay, so what happens here is that, first of all, this function that I'm integrating here is supported in the interval j to the 2 minus l to j plus 1 to the 2 minus l. So there's two possibilities. Either this interval is included in that larger interval, right? This interval is larger because this is an interval of side lengths 2 to the minus k, whereas this is supported in an interval of side lengths 2 to the minus l, and l is greater than k. Now, these dialectic intervals are nested. So there's two possibilities. We have either this interval j to the 2 minus l to j plus 1 to the 2 minus l does not intersect the interval m 2k plus 1 to m plus 1 to 2k minus 1, or if it intersects the larger interval, then it has to be included in the largest interval because of the way these intervals are constructed. All right, so, okay, if there's no intersection, then you're integrating 0, and if there is an inclusion, then you're integrating 2l over p half of the time, and minus 2l over p the other half of the time. So you're integrating a function over its full support, and this function has mean 0. So no matter what, you have that e 2 to the k, e 2l plus j is 0. It's constantly equal to 0 if L is greater than K. Okay, now let's see what happens if K is greater than L. So there's two possibilities. Either T is in the support of the E2L plus J, or it's not. If it's not, then I'm integrating 0 here. So really, I only care about what happens on the support of E to the 2L plus J. And if I'm on the left side of that support, let's look at that first. Right, so that corresponds to multiplying this by the indicator function of j 2 to the minus l, j plus 1/2 2 to the minus L. So if I'm somewhere here for some values of m, then what am I integrating? Well, whenever I'm here, so that means this small interval, if this is non-zero, then this small interval has to be included inside this interval. So what I'm integrating on that interval is just 2L upon P. And I'm integrating that on an interval of side lengths 2 to the minus k, and I'm multiplying by 2 to the k. So this entire thing here, whenever this is non-zero, has to be equal to 2L upon P. And then the sum in M really sums up to 1. So I'm really getting just this indicator function times 2 to the L upon P whenever I am in this interval. And then if I'm in the other interval, here's a half of the interval where I'm non-zero, then what do I get? That's j plus 1/2 till j plus 1, 2 to the minus L. So if I'm on this interval, then what I'm integrating, again, it's constant because this whole interval here is bigger, or this interval here will contain this interval if this is non-zero. Right? If not, there's an empty intersection, and so the multiplication of the indicator function gives us 0. So whenever I'm on here, really I'm integrating only on this part, so I'm integrating minus 2 to the L upon P, constant on the small interval. And then, if you're neither, as I was saying earlier, if you're neither on that interval nor on that interval, then you're integrating 0 anyway, because there's no intersection between, well, because what you're integrating away from the support here will be 0. So putting all of these two things together, you get back your e to the 2l plus jt. So it really looks like e to the 2k is a projection. It takes the vectors that corresponds to a n of the form 2l plus j for a larger L, and it sends them to 0, so it kills all the ones after 2 to the k, and then the ones before, it sends them to themselves. So it really looks like a projection, except we haven't quite treated the case k equal L yet. So let's do that now. Okay, so if I'm in the situation where L is equal to k, and I'm computing e to k of something of the form e to k plus j for some j between 0 and 2 to the k minus 1, then what happens is that at any point t, right, this integral is going to be non-zero only if I'm on the interval corresponding to j, right? Because this is 0 except on the support of e to the 2k plus j. So what I'm going to get here is really just the indicator function of j 2 to the minus k, j plus 1, 2 to the minus k of t, times the average of the function on that interval, the only interval where the integral of e to the 2k plus j is non-zero on the interval of that form. J 2k to j plus 1 to the 2 minus k times e 2k plus j of s ds. Yes, but on that full interval, e to the 2k plus j of s is as integral 0 on its support, right? Because it's 2 to the k over p half of the time and 2 to the minus k over p is a half of the time. So this is also 0. Okay, so all in all, we have that e to k of e to l plus j is equal to e to l plus j whenever l is strictly smaller than k, and it's equal to 0 otherwise. So these operators e to the 2k are not exactly the partial sum projection into our basis, but they're very close to that. Let us now define p2k plus j for some k in n and for some j between 0 and 2 to the k minus 1 to be the following. So I'm going to take that at a point t to be e2k plus 1 of f at t if t is below j plus 1 2 to the minus k. And then I'm going to take it to be e2k of f of t if t is above that value. Right, now the point of doing that is that p2k plus j of e2k plus m now, for any m, in 0 to k minus 1, is going to be what? Well, it depends on whether m is above j or below j. If it's below j, then I'm really applying e2k plus 1 whenever this is non-zero. And e2k plus 1 of little e2k plus m just gives e2k plus m back. That's if m is below j. Now, on the other hand, if m is above j, then what I'm applying, actually, that's if m is less or equal than j, but if m is strictly above j, then I'm applying e2k to little e2k plus m, and then because of what we've done in the case L equal k above, I get 0. So this is no projecting such that within the scale k we only keep those elements up to j. Now, if I look at p2k plus j of e to l plus m, this is going to be e to l plus m for any l in n whenever l is below k, and it's going to be it's going to be 0 if l is above k, also by the above reasoning applying to e to k plus 1 and e to k. So really what we have now for any x in x is that and for any n and m in n, let's say with n greater than m, we have that the sum x en n equal 0 to capital M. So really here I would want en star, in general, but in this particular case en star can be identified with en. What we have here is that this is equal to Pm applied to the sum n equals 0 to capital N of x en, because what this P capital M is going to do, it's that it's going to send any element in that larger sum that comes after capital M to 0, and it's going to keep all the elements up to capital M unchanged. So this is really like partial sum projections. Now the question is, well, these are the partial sum projections. So the question really is whether or not these operators Pm are bounded as linear operators on LP, bounded uniformly in capital M. Now, to prove that, notice that Pm of f, because of the way it's defined, right? You replace the function by its averages at one scale or another, depending on where you are in the interval. So one thing for sure is that just controlling the function by its supremum, you get that Pm of f of t is smaller than the sup of f for every t in 0, 1 and for every f in L infinity of 0, 1. So this tells me that Pm extends to a bounded linear operator on L infinity. And more importantly, its norm as a bounded linear operator on L infinity is smaller than 1. Okay, now on the other hand, you could also control the integral over a small subset by the integral over the entire set. And so you can show from that that if you take the L1 norm of PMF, this is controlled by the L1 norm of F. So you also have a bounded linear map on L1 with norms smaller than 1. So by the Marcinkiewicz interpolation theorem that we've seen before, we get that PM, so there should be no F here, so there's a bounded linear operator on L1, PM extend to a bounded linear operator on LP with norm smaller than 1. And so when you plug that back in star, you get that En has to be a basic sequence. It satisfies the two properties that characterize basic sequences. Excellent. Now let's show that this is indeed a basis. So in order to do that, let's first consider f a continuous function on the closed interval 0, 1. Now what happens, let's say for k in n, if I look at e2k of f of t minus f of t for all t in 0, 1. Now this is going to be equal to, well, smaller than the sum of the indicator function of j 2 minus k, j plus 1, 2 minus k of t, j running from 0 to 2k minus 1 times what? Times 2 to the k times the integral j2 minus k to j plus 1, 2 minus k of f of s minus f of t ds. Right. And now I can use the continuity of f on 0, 1, and so it's uniform continuity to say that therefore for every epsilon there exists a k in n such that for all k greater than this capital K and for all t in 0, 1, e2kf of t minus f of t is smaller than, than the sum j equals 0 to 2k minus 1 of this indicator function of t times what's in here, which is going to be smaller than epsilon. Okay, and there's only one element in that sum that is non-zero, so this thing is equal to epsilon for every value of t. So what does that give me? That gives me that for all f in C of 0, 1, and for every epsilon, there exists a k, such that for little k above that capital K, the LP norm of E2k of f minus f, right, you can integrate that on 0, 1, is smaller than epsilon. Okay, but now the continuous functions are dense in LP of 0, 1, so for every f in LP, so let's let f be in LP of 0, 1, and let epsilon be a positive number. Now I can pick g, a continuous function on 0, 1, such that the LP norm of f minus g is smaller than epsilon. And so once I've done that, I get what? I get that for every f in LP and for every epsilon, there exists a capital K, such that above that capital K, E2k of f minus f in LP is smaller than E2k of f minus g in LP by triangle inequality, plus f minus g in LP plus E2k of g minus g in LP. And so for g, the continuous function, that is epsilon away from f. And so this whole thing, because the E2k, that's extremely important, we've proven that these things have norms uniformly bounded by 1. This is smaller than 2 epsilon plus E2k g minus g. And so the whole thing can be made smaller than 3 epsilon by taking k large enough. And what was E2k of f? Well, it's a finite linear combination of elements in the basis. So we've proven that the span of the EJs, any element f in LP can be approximated by an element in the span of the EJ. So the closure of that in LP is all of LP. And therefore, the ENs form a basis of LP. So to prove unconditionality, we will prove the following estimate. So we will prove that for every capital N in N, and for every choice of real numbers AK, for every choice of signs, epsilon k, we have that the sum of epsilon k ak ek, k equals 0 to n, is controlled by a very specific constant, so in LP, and the constant is going to be maximum of p prime minus 1, and that happens to be the best possible constant times the norm of sum of ak ek without the epsilon n. So this is what we're going to prove. Let's call that U for unconditionality subscript P. Okay, so that's what we want to show in this next part of the proof. Now the first thing is that we're going to show that if UP holds for all P greater than 2, then UQ holds for all Q smaller or equal to 2. So without loss of generality, we will be able to assume that P is above 2. Alright, so let's first see that duality argument. So the duality argument goes like that. We're going to define, let's call that Gn. That's going to be the sum of the AK, epsilon k, AK, EK. And let's define Fn to be the sum of the AK, EK. Okay, now one can pick a Gn tilde in LP prime such that the integral of Gn tilde is exactly the norm of Gn in LP. That's because we have the existence of norming functionals by Anne Banach. But this Gn is a function, Ek is a basis of LP prime, and the Eks are orthogonal to each other in the L2 sense. So that means that there has to exist a sequence AK tilde, k equals 0 to n, such that, so a sequence of real numbers, such that Gn tilde is really the sum of AK tilde Ek, k equals 0 to n. If there was any other Ek in the description of Gn tilde, well, when you integrate it against Gn, it would give you 0, so this won't contribute anything to this integral. So you might as well assume that your Gn tilde is of this particular form. And indeed the norming function will have to be. Okay, so when I try to compute the norm of Gn in LP, I have to compute the integral Gn times Gn tilde. And what is this integral? It is the sum, k equals 0 to n, of epsilon k, ak times ak tilde, times the integral on 0, 1 of ek squared of s. ds, right? And that's because, again, let me remind you here that the integral of ek ej is delta kj by the construction of the basis. So, right, if they have disjoint support, then of course the integral is 0. If they are the same, then the integral is actually it's not delta kj. Because I've normalized things to be to have norm 2k upon p, so this is 2 to the 2k upon p times delta kj. All right, so the point here is that because of this orthogonality property in L2, we can rewrite that as the integral of the sum of ak ek, k equals 0 to n, times the sum j equals 0 to n of epsilon k, a tilde k, ak, ek. And so what I've done is that I've moved the epsilon j from being next to the AK in the definition of Gn to moving them into the Gn tilde. Now you can apply Hölder, and Hölder will give you that this is controlled by the LP norm of the sum of AK EK, which is what you want, times the LP prime norm of the sum of AJ tilde EJ in LP prime. So if you have UP prime, then you get the maximum of P prime minus 1 times the norm sum AK EK P times the norm of Gn tilde in LP prime. And remember that Gn tilde was a norming functional, so I forgot to say that here, but of course the Gn tilde, being a norming functional, must have norm 1. So this is 1, and then we've proven UQ, or UP for P less than 2. It's a bit confusing here. I should have called that, I should have said let P be below 2 here, and probably this is cleaner if I write Q here and P there. Right. So I have a P less than 2, and I get UP for P less than 2 by having UP prime, and P prime is going to be greater than 2. Okay, so that concludes the proof of this little remark, and so from this point onward, without loss of generality, we can assume that P is greater or equal to 2. Okay, so we have a P greater than 2 now, and what we need to show is that for all n, so we need to show that for all n in n, the integral from 0 to 1 of, if I reorganize things a little bit, phi p of fns gns ds is non-negative, where phi p, right, what I want for my inequality is phi p equal p minus 1 raised to the p times x to the p minus y to the p, right? If that's non-negative, then I can bring the gn to the p to the right-hand side, and it is smaller than p minus 1 to the p times norm of fn to the p, my integral of fn to the p. Okay, for all xy in R. So this is what we want to show, just slightly rewritten, and there are many ways to show that. The most classical one uses a part of harmonic analysis called Calderon-Zygmunt theory, but that's not what I'm going to show you. What I'm going to show you is a proof due to Burkholder in the 1980s that uses what's called a Bellman function argument. Now, I want to show you this argument for several reasons. One is that, well, we can do it. It's fairly elementary. It doesn't require us to bring in a lot of harmonic analysis into the picture. It's elementary, but it's extremely smart. And the other reason is because this type of arguments have become extremely popular in the last, what is it now, 10, 15 years probably. They've been very much popularized by a group of mathematicians named Fyodor Nazarov, Sasha Folberg, Sergei Trail. So they've used this idea that can be traced back to this argument of Burkholder about unconditionality of the Haar system, but also of certain Martingale inequality back in the 80s, and they've used these ideas everywhere for all sorts of sharp estimates in analysis of PDE, in harmonic analysis, and in really quite a range of questions. And the argument is pretty striking. And what is the basic idea of the argument? Well, the basic idea is that although I want to prove a certain inequality that involves this function phi p, I could prove a similar inequality for another function that I could choose as long as it is smaller than phi p, or say up to a constant. So this is the key remark / idea here. So the idea is the following. Imagine that you can find a lambda, and you can find a function phi, little phi, c2 of R2, that is such that phi p of xy is always greater than lambda phi xy on the one hand. And in the meantime, we have that for every n, in n, phi of fns gns, if I integrate that, then I get something non-negative. Well, if I can prove what I want for a phi that is smaller up to a constant than capital Phi p, then I get my result. So having this would imply the result. So there is a bit of freedom here. I don't need to take this very specific choice of a function phi. I just need to prove the inequalities I want for every n for a little phi that is dominated by the capital Phi p. So I'm going to hunt for such a little phi. That's what we're going to call the Bellman function. So here's a condition here. Whatever little phi I'm going to suggest will need to satisfy this domination condition. Right. And what we want to show is we want to show this sequence of inequality for all n, and I'm going to call this sequence of inequality Bn of phi. Right. So I need to find a phi such that Bn of phi holds for each n, and my phi has to satisfy the domination condition. But there's flexibility in choosing that phi. And what we're going to see is we're going to derive a sequence, no, not a sequence, but we're going to derive a few properties that the phi needs to satisfy. Crucially, there would be a partial differential inequality. And then by finding some phi that satisfy all these constraints, we'll have Bn phi for some phi, and that would imply our result. That is, in essence, the principle behind the Bellman function arguments. Okay, so we want to prove Bn phi for some phi and for all n. Most likely we're going to do it by induction. So let's start with capital N equal 1. Okay, so what is the B1 phi condition? B1 phi is really saying that the integral 0 to 1 of little phi of epsilon 1 a1 e1 of s, comma a1 e1 of s ds has to be non-negative. So I want to ensure that. Okay, fine. Let's put a condition on phi that will guarantee that for sure. Let's look for a phi that is of the form of some, well, that is such that phi of xy is just the same as phi of mod x and mod y. So the function phi doesn't care about the sign of its component of these variables. And let's also assume that phi on the diagonal, phi xx, is non-negative for all x. Now if I have that, then I will have B1 phi, obviously, just by properties of my function little phi. So this is like a positivity condition on phi. All right, and I'm going to impose that. Now, of course, if I get away with imposing more condition on phi in order to prove whatever I want to prove, I'm going to get a set of conditions that maybe are so constraining that there is no phi satisfying all of them at the same time. But so far, so good. We want a phi that is dominated by capital Phi p and that has this structural positivity condition that we've written here. And of course, the whole point of this proof is that I'm going to come out with a set of conditions on little phi, and then I'm going to prove that there is a phi, I'm going to exhibit a phi for that matter, that does satisfy all of these conditions. Okay, now if B1 holds and I want to prove Bn for all n, by induction, all I need to prove is that Bn minus 1 phi implies Bn of phi for any n non-zero. Okay, now there's another nifty idea here, which is in order to prove this induction statement, we're going to embed it into a continuous family of similar statements in order to bring in calculus methods. So we're going to define capital F of t to be the integral from 0 to 1 of phi of 1 minus t gn minus 1 of s plus t gn of s, comma 1 minus t fn minus 1 of s plus t fn of s ds. Now the point is the condition bn minus 1 of phi is nothing but the condition f of 0 greater or equal to 0, whereas the condition bn of phi is nothing but the condition f of 1 greater or equal to 0. This f of t is defined for f for all t in the closed interval 0, 1. So it suffices to show that f prime of t is greater or equal to 0 for all t. All right, because if I can show that for that f of t, then I will have that bn minus 1 of phi, namely f of 0 being greater than 0, implies that fn is greater or equal than 0 because ft goes to f of t will be non-decreasing. So we want to prove this condition on the derivative of f. Okay, let's compute f prime t. So f prime t is the integral from 0 to 1 of gn minus 1 s minus gn of s, actually that's the other way around, minus g1 plus gn, times the derivative in the first component of 1 minus t gn minus 1 of s plus t gn of s, comma 1 minus t fn minus 1 of s plus t fn of s, and then plus fn of s minus fn minus 1 of s times the same thing with the second derivative, the derivative in the second component of phi. And all of that ds. Okay, now phi prime of t more, you can rewrite this. This is equal to an times the integral from 0 to 1 of en of s times epsilon n d1 phi of the entire thing. Of the entire thing. Let's keep it like that for now. Plus d2 phi of the entire thing, ds. Excellent. Now, what is it at 0? At 0, I want to show it's always non-negative. So let's first of all check it at 0. At 0, this is an times the integral from 0 to 1 of en of s times epsilon n times d1 of phi of gn minus 1s fn minus 1s, and then plus d2 phi of gn minus 1s fn minus 1s ds. Now that's where somehow the miracle happens, because this entire thing here is constant in s on the support of en. Right, because the way these things are defined, gn minus 1 and fn minus 1 do not have an en component. They only have component for ej's with j smaller than n, right? And so at this higher level in the Haar basis, all the functions will be constant on a tiny support like the one of en. So what I have here, this entire thing within a bracket, although it looks like a function of s, on the support of s, where we are, because if not, en s is 0, this is a constant. So really, this is a multiple of the integral of en s. But the integral of en s, right, if all of this thing is constant, I can put out that constant, and the integral of en s is 0. So this whole thing has to be 0. So f prime of 0 is definitely non-negative because it's actually equal to 0. That's what I get from the information that I have at t equals 0, that is to say at n minus 1. And then I want to go from capital N minus 1 to capital N. So, all right, now I have f prime of t at 0, it's equal to 0. I'd like it to stay non-negative. One way to do that, looks like we're going nowhere with this, but in fact we are going somewhere. One way to guarantee that would be to guarantee that the second derivative of f is non-negative. Right, if this is true, then f prime of t will be non-negative, and the result will follow. Right, because f prime t being non-negative will guarantee that bn minus 1 implies bn, and then will be done by induction. So really what we need to show now is that f second of t is non-negative. Well, let's compute f second. Now, computing f second is going to be a really great idea because f prime still had this sign epsilon n coming in, but this is going to come twice into the computation of fn second, and so this sign business will essentially disappear. So what we have here, okay, when I compute the second derivative, I still have my an here, and then I start differentiating, and so for the first term, I'm going to get epsilon squared en of s squared times d1 squared of phi, of still the entire expression inside the phi. Then I'm going to have the same second derivative for the derivative in the second variable of phi, and that's going to give me an ens squared. Oh, I forgot an an, so both of them come with an an, so you get an an square in here, and you get en squared d2 phi of the whole thing. And then we have some cross terms, and the cross term will be 2 en of s squared, but then we get an epsilon n only once, times the mixed derivative d1 d2 of phi of the whole thing, ds. So that's what f second looks like. Now, how could I guarantee that f second is always non-negative? Well, one way to do that will be that, given that I have an an square at the front, so the sign of an doesn't matter anymore, so I would get f second of t non-negative if I could guarantee that whatever it is I'm integrating is always non-negative. And I'm going to guarantee that, completely irrespective of n, by putting a new condition on phi, which is a differential inequality. I'm going to ask phi to satisfy d1 squared of f of phi xi y plus d2, that was a square here, of phi xy. I want that to be always greater than 2 times the absolute value of d1 d2 phi of xy. And I want that for every x and y in R. So if you have this differential inequality, then phi second will be non-negative for every t. So what have we got? So we have that if there exists a phi C2 that satisfies the domination assumption, the positivity assumption, and the differential inequality, then the proof is complete. So we've reduced this problem about some inequality in LP spaces to a fairly difficult looking calculus problem, but just about really calculus of functions of two variables. We need to find a function that satisfies these three assumptions, probably the hardest one being the differential inequality. And here is the magic. The magic is that if you pick phi xy to be x plus y raised to the power p minus 1 times p minus 1 times mod x minus y, then this does satisfy the domination, the positivity, and the differential inequality. And I am not going to do it. This is an exercise in calculus, or this is something that is even so formal that you could just put it in CAS system if you want to just reassure yourself that this is indeed working, or you do the computation by hands, which is what people do in all of the Bellman function arguments. But once you've guessed what the right Bellman function should be, and there are ideas coming from optimal stochastic control to tell you what the guesses should be, but it was fairly miraculous at the time of Burkholder. We don't really know how he thought about that. But once you have the right function, then you check that it satisfies all the assumptions that you wanted, and this concludes the proof. So we've shown that the Haar basis is indeed, well, we've shown up to this calculus difficult exercise that I'm not going to do, that the Haar basis is indeed a unconditional basis of LP for all p strictly between 1 and infinity. Now, this proof by Burkholder shows that it's unconditional and even gives you the best constant. You can prove that the constants in those unconditionality inequalities cannot be improved. The Haar basis is an example of a more general family of bases that are very important to analysis called wavelet bases. And the idea is that these are bases that you obtain from a function that we call the mother wavelet, which is this function, which is 1/2 of the time, and -1 the other half of the time, just by a combination of dilation and translation, right? Every element of the basis is obtained from that first element through applying different dilation and translation operators. Now, this basis turns out to be extremely important in the sense, for instance, that when you look at operators that are built from differentiation operators, so these are the operators that one studies in harmonic analysis, or the operator that one studies when one wants to look at the relationship between data and solution to some partial differential equations, all of these operators happen to always be close to a diagonal operator when decomposed into a wavelet basis. So these are bases that are very effective in analyzing differential operator or questions arising from Fourier analysis. Now, when I say these bases and when I call that a wavelet basis, I'm slightly cheating because, see, this mother wavelet here is discontinuous, and that causes all sorts of problem and applications. So for a while, if you go back to the 60s and 70s, people were wondering whether or not you could create an analog of the Haar basis, but starting with a mother wavelet that is smooth. And the answer is yes. That was some very important discoveries of Ingrid Daubechies on the one hand, and Yves Meyer on the other, and the development of wavelet theory. So there's a whole family of such bases that one can construct. One can make sure that every element of the basis is smooth, and they form unconditional basis of LP with respect to which analyzing differential operators or solutions of partial differential equation can be done very effectively.